What is rock physics? In the strict sense, rock physics means using physical methods to study the properties of rocks. We treat rock not just as stone, but as a solid material whose behavior we can measure, model, and predict. Geologists and mineralogists look at rocks in two ways. Macroscopically, what we see in the field, layers, faults, textures. Microscopically, what we see in the lab, individual mineral grains, pores, and microcracks. But rocks also have quantitative physical properties, just like any other solid. Density, elastic stiffness, porosity, permeability, electrical resistivity, magnetic susceptibility, thermal conductivity, and so on. These are the numbers that tell us how a rock carries stress, fluids, heat, and fields. From the geophysics side, rocks are the medium through which we measure the Earth. Seismic waves, gravity, electricity, magnetism, heat flow. All of these signals pass through rocks and are distorted by their properties. To interpret those measurements correctly, we must understand how rocks respond. That is why rock physics, sometimes called petrophysics, is the bridge between many branches of geoscience. Geophysics, lithology, petrography, hydrogeology, and rock mechanics. It connects what we see in outcrop and under the microscope to what we measure with instruments and models. So what is a rock exactly? In geology, a rock is any natural aggregate of minerals with one or more mineral phases. Rocks make up the Earth's crust and mantle, and also the crusts of other planets, moons, and asteroids. We usually group them into three main families. Sedimentary rocks, formed by the deposition and consolidation of weathered material or by chemical and biological precipitation. Magmatic rocks, formed when molten material, magma, cools and solidifies at depth or at the surface. Metamorphic rocks, formed when existing rocks are transformed by high temperature, pressure, or reactive fluids. Depending on how tightly the grains are bound, we also distinguish loose or soft rocks, like sand, from hard rocks, like sandstone. Ores are simply rocks where useful metals have accumulated to economically significant levels. But the story of rock physics does not start at the surface. Our planet, like other terrestrial planets, is built from rocky shells and a core assembled from dust and gas in the early solar nebula. Gravity pulled material together, the proto-sun ignited, and heavier elements stayed close to the sun, forming the inner rocky planets, Mercury, Venus, Earth, and Mars. In that young disk, tiny proto-rocks formed, droplets and dust clumps called CAIs and chondrules. They melted, cooled, and collided, slowly building larger bodies. Over time, metallic and non-metallic elements condensed at slightly different stages, creating different meteorites. Their impacts and aggregation ultimately produced planets with a layered, shell-like structure, core, mantle, and crust. As the early Earth grew, it heated up. From meteorite impacts, from gravitational compression, and from the decay of radioactive isotopes. This drove melting and separation. Dense iron sank to form the core. Lighter silicate material rose to form the mantle and crust. The result is a differentiated rocky planet where only a small fraction of elements, the lithophile elements, ended up in the accessible crust. Rock physics is how we quantify all of this. It gives us the effective properties of these heterogeneous mineral mixtures, their density, elasticity, permeability, thermal behavior, and radioactivity, so we can model how they behave under stress, fluid flow, and temperature. For GEIOS technologies, this is the foundation of Geinesis, the origin of energy. Rock physics tells us how rocks store and transmit heat generated over billions of years, how fractures and pores guide fluids like water, steam, and hydrogen, and how the physical fabric of the Earth controls where and how we can tap that energy. Before we talk about advanced nanomaterials, phonons, or radiogenic heat, we start with this simple question. It is the language that lets us read the solid Earth and trace the true origin of the energy we want to harness.